Hello, this is the video on post-order traversal. We have already covered pre-order and in-order iteratively with a stack. It is a recursive thing, but we are doing it with while loops. The In a recursive function, we exploit the call stack. So we'll be using stacks, and but the call stack, the actual call stack, has return pointers that we do not have. So we use a clever way to partition the function into two parts, and we run it. So I'm just going to summarize it. When we start calling onto a certain node, we come here, we print itself, we make a call, and then we put the rest of the function on a stack so that we know we can return and call the right child. Okay, that was the strategy with the pre-order. In Now remember, after we make a call to the right child, we don't actually return back to the return pointer true in our implementation because we don't have to. Okay, there's nothing to do after here. The same applies for in order. The function technically has two return pointers because this is a function call, that is a function call. After you leave the function, you have to return here. After you leave the function here, you have to return here. But we can technically ignore the second return pointer, and that's why we can implement this easily. So we partition the function like so. So whenever we make a call to the left child before leaving, we put the tree node on the stack, and we know to be on the stack means we must continue from here. So when we pop off the stack, we print self and make a call to the right. Now, post order is a little bit different because over here you also have to leave the function two times, but in this case you cannot ignore the second return pointer because you must come back here in order to know what in the world you are printing. You have to print self, but you have to know what self is. So in order to know that, you must come back here. That's why the execution of the implementation would be a little bit different than the ones before. Now, I have drawn out the tree that we had been using, and we are gonna simulate the call stack right now, but we are gonna have to think about how to implement that differently because, again, we cannot store a return pointer in a stack without significant effort. So for now, this is the call stack. The call stack was made. The call was made to one. So we are executing here. Okay. Uh, so what happens when we make a call in the post order scenario? We immediately make two calls. We make a call to the left child, to the right child. I mean, we make a call to the left child. Okay. We put a return pointer and leave. We don't make a call to the right child just yet. So we make a call to the left child too. Okay. Before we leave, we say return pointer one. Okay. So whenever we come back here, we must continue execution from over here. Okay. We have to make another call and print. So that's the idea. Let's continue. So again, we are executing on the top of the stack. Excuse me. Uh, so I'm not going to draw an arrow. So in the call stack, you're always executing at the top of the stack. Okay. Now, again, we are now making a call to the two. What does it mean to make a call? It means we make another call to the left child and put the rest of it on a stack and indicate where we should return. So I leave two, and I must return on return pointer one again because I haven't called the right child yet, and push the four on the stack. Now we are executing at four. At four, we do the same thing. We make a call to the left child. Left child of four is null because there's nothing here, and my return pointer is one. Okay. Now at the null, null is the base case, so we return and do nothing, and now we are executing here. Now look at the return pointer. Return pointer is at return pointer one. It means I have already made the left call. Now I must make the right call. Let's do that then. So the right of that. So now this time, before leaving the function, I will update the return pointer. I will say, okay, return to, that's R, that's the P, return to return pointer 2, and then make a call on the right child. Now this call again finishes with nothing because again, that's the base case. And then we return to 4. Now, where do we return? At return pointer 2. Where is return pointer 2? Return pointer 2 is right there. What do we do after return pointer 2? We print self. Okay, this is our first print. So let us do that. Excuse me. Okay, so this is our first print. So we just printed 4, and let me remove those. And then the function execution continues. After printing, we are done. We close the function, we pop the whole thing off the stack. This is the call stack again, this is not our stack. Okay, now we have to continue at the function call for 2 at return pointer 1. What was at return pointer 1? It means that we are done making a call to the left subtree. Now we have to make a call to the right subtree. Let's make a call to the right subtree and so I'm gonna make a call and I'm gonna update the return pointer so that I return at return pointer 2 this time. Okay, so we have to come back to the function twice. So this is the second time we will come back. Okay. We are making a call to the 5 and then we execute. We are making a call on its left child, and then we have a return pointer 1, indicating that I have made a call to the left child. Whenever you come back to this function, do not make another call to the left child. You already made that right here. Okay, so 6, we are making a call to 6. What does it mean to make a call? It means to put your uh, left child on the call stack and then give it a return pointer 1. That is supposed to be an this function returns, we resume execution over here. So when we are here, it means we are done. We returned from after making the call to the left child. That's we are returning. So now we must not make another call to the left child, but we must make a call to the right child. Who's the right child of 6? That's a null. Okay, we make a call, but before we go, we update the return pointer to 2 to indicate we come back after making a call to the right. Let's make a call to null. Making a call to null is the base case. We do nothing. And then we come back here to return pointer 2. What do we do at return pointer 2? We print self. Okay, this is our second print in this whole tree. We are going to print 6. And then the function pops up. Now at 5, we have return pointer 1. What does it mean to be return to return pointer 1? It means we are happy. We have already we are done with the left subtree. We must make a call to the right subtree and change the return pointer. Okay, so let's do that. The right subtree is the node is 7. Return pointer, I return to return pointer 2. Okay, we are making a call to 7. We are executing this, the very first line. We make a call to the left child, which is null, and return pointer 1. Okay, and then we execute this call. This call doesn't do anything because this is a base case. This simply returns. It returns to over here. What does it mean to return pointer? It means you have finished the left child. Now you are supposed to call the right child. Let's call the right child. That's also null. Okay, now let's and the return pointer is 2. Okay, because it means I am the whenever I come back, I continue from after calling the right child. Okay, now making a call here, it just simply pops off the stack because that's null base case, and so I return here. Okay, I return at return pointer 2. What do we do when we return at return pointer 2? We print the self. Let's go ahead and do that. We print 7, and then after printing, we close the function. We come back to 5, return pointer 2. Return pointer 2 means I am done with both calls, so I will just print self. I printed self, I'm happy, close out. We return to function 2 at return pointer 2. What does return pointer 2 mean? Return pointer 2 means I am done with both my left and right children subtrees. I now print self. I pop that off the stack. And I don't think it's a problem if we continue. Let's continue. Uh, The video will be a little bit longer, but I am assuming you are here for that. There are a bunch of other good tutorials out there. Anyways, so we return to function one, return pointer one. That means we are done with the left child. Now we must make a call to the right child. Now right child is 3, and then I update before leaving this again. Now whenever I return again, I must change this. Um, excuse me. I must print this. Yeah, making a call to 3, and then 3 will call its left child, which is null, return pointer 1, and then null will pop off. I will come back to 3. I will make a call to its right child and put return pointer 2. 8 will make a call to its left child with a return pointer 1, and 9 will call its left child with return pointer 1, and then after this call pops off, uh, I am making, I'm gonna have to make a call to the right child. So right child is also null, and whenever I come back, I'll come back at return pointer 2. I execute the function on null, do nothing, and then when I'm back here with return pointer 2, I only have left to print. I'm done with both calls. We are back at 8 at return pointer 1, so we know that we have already called the left subtree. Let's call the right subtree of 8, again null, and update the return pointer to return pointer 2. The null simply pops off the stack because that's a base case. We return doing nothing. We have returned to 8 with return pointer 2, print the 8, and pop it off the stack. We have returned to 3 with return pointer 2, print the 3, pop it off the stack. We have returned to 1 with return pointer 2, print the 1, pop it off the stack. Stack is empty, call stack is empty, we are done. Okay, now let's try to think about how we are going to implement this in our code. There are multiple ways of doing it. The way I learned to do it is by the two-stack method, and it makes sense to me. The insight of this method comes from the fact that you you only print after you are done with both your left and right children calls. Okay, so the printing is done after. So we made the call to 1 at the very beginning. It was the root. And notice that after we have processed all its subtrees, we have printed 1. Okay, it's the same idea with all of this. So after we print the whole subtree, we print itself. That's the idea. Now the printing is always after the calls. So we can have two stack. The first stack, we can call it a call stack, okay? Call stack. Now this call stack to me represents return pointer 2. What we do is we push both the calls over there, and then the self, we push it to another stack because we know this stack will be below the previous stack. Okay, so printing is always done after the calls to all my children have been successfully made. So I'm drawing this below. This is the print stack. Now this is a clever way of avoiding having to come back to return pointer 1. So instead of coming back to the same function after return pointer 1, we know that we have to make a call to both of them. So let's group the thing like this. We're gonna do this, and then we are going to push both of the left and right children onto some kind of a call stack, and then push the self into another stack which is below both of them. Okay, we are going to process this printing stack after the recursive calls have finished. Okay, so that's the idea. So this is our call stack. Okay, now Whoops, I don't think I drew it well. Okay, anyways, let's start. Now we are gonna make a call to, so in this implementation, making a call means pushing whatever you're making a call onto this call stack. Okay, so we push one. Now we are gonna make a call here. What does it mean to make a call? In our case, to make a call means, okay, let's do it this way. To make a call means to put yourself on the printing stack, because we are going to return to this after what? After I'm done with both my children, both my left and right child. That's why. So this is the trick to this, because only after you're done with this stack, you will come here. We cannot keep one over there because that will interleave the roots. So we are separating it out. We don't want the selves interlaced. We are gonna pile on the selves over here, on the print stack. Okay. Now let's make a call to whatever is on top of this call stack, which happens to be 3. We are gonna make a call to 3. The 3 is too big. I'm gonna make it smaller. So we are gonna make a call. So we are processing the call to 3. What does it mean to make a call to 3? We print both its children. I mean, we make a call to both its children, null and 8. And I've already pushed 3 onto the printing stack. Okay, let's make a call to, now let's process 8. Okay, this is a function call. We put itself on the printing stack, because after I'm done with both the children, I come back and print. Now let's call on its children, 9 and null. Now, like usual over here, when we call on the null, we return and do nothing. Now, when we come here, again, this call stack means we have never processed this. This is the first time we are calling the function. So every time we pop things off the call stack, we are not in the middle of the function, but we are in the beginning of the function. Okay, so we uh, push it onto the print stack for printing at the very end, and we make a call to both of its left and right children. Null, null. We haven't printed anything yet because we haven't gone there. So null, we process and we push that out of the stack, push that out of the stack, push that out of the stack. Now we have to make a call to 2. Okay, what does it mean to make a call? To make a call means copy yourself over. Ooh. Push yourself to the print stack, and then put your children here. Children are 4 and 5. Now we are making a call to 5. What does it mean to make a call? It means to push yourself onto the printing stack and then make a call to your children, which is 6. That's too big, and on the side, it is 6 and 7. Okay, now we are making a call on 7. What does it mean to make a call? It means to push yourself on the stack and give me your children. Null, null. Okay. The null, we pop this and see that it's null, we do nothing. We see this is null, we do nothing. But we see that this is a 6, we have to work on it. We put it on for printing, and then we, did I make a big mistake? I hope not. We put it on here for printing, and then we push both its children. What are the children of 6? Null, null. So we check. This is a base case. We do nothing. Null, null. Okay, we are going to make a call on 4. Now, what does it mean to make a call? We put the 4. Whoops, the 4 didn't come through. We put the 4 on our return call stack, and call on the children. Null, null. Okay, I think we're done. So these pop up the stack. Now the call stack is empty. Now, what does it tell you? It tells you you are done making a call to all the children, and printing them. After you've printed them, now you have to print 1. The 1 is at the very end. You see it is at the bottom of the stack as expected. Now let us pop things off the stack and print. I pop off 4, and you know what? I think I can do this. I pop off 4 and I print. I pop off 6 and I print. I pop off 7 and I print. I pop a 5 and I print because this is my printing stack. I left 5's tails upstairs. Sorry 5. And then I pop things and then I continue printing them on the here. And that's 5's tail belongs to 5. And notice that I got the exact same result as before, like so. 4, I cannot read because of my toolbar. 4, 6, 7, 5, 2, 9, 8, 3, 1. Same. So this is the idea. I hope that's clear. I'm going to show you my code that implements this over on the LeetCode website right here. So I have a call stack. It is a new stack of 3 nodes. There is a print stack. It is a stack of integers. I could have made it 3 nodes, but again, it's just an implementation choice. I choose to put integers. And here is a list of results. Now that I think about it, 3 node would have been better. Now, if I don't have a tree, I print my results are empty. I return the empty result. Now, otherwise, we push the root onto the call stack and we start working. We don't set anything to the current because, again, that's empty. Now we go until the call stack is empty. This is the while loop for call stack. Children, afterwards, we are gonna pop and print the print stack. Okay, so every time we come here, we set the current to, we pop from the call stack, we take the first element there and we process it. What does it mean to process? We push the left child onto the call stack. And the current is no longer on the call stack. Okay, we push the current onto the print stack, and we make 2 calls to the left and right children of the current. Okay, the we don't push on the nulls to the call stack because I don't want to. Oh, in yeah, we could have, when I went through on the whiteboard, I said we push nulls, and we could have implemented it as to check for nulls. Over here, I implemented it a little differently. I don't even push the nulls on the stack because they're nulls. I don't like nulls. So if they're not null only, then I push on the stack, right? Uh, Left and right. And then before leaving the current node, I push it onto the print stack because I know uh, whenever I come back here, it means I'm done with calling all those. So this while loop calls all of the functions. And what does it mean to call? Let me just quickly go back and show you. Whoops. Okay. It means you come here, you do these two. You make a call, you push both of your children onto the stack, and you go yourself and wait on the print stack so that you can come back there. That's exactly what we are doing. And while the print stack is not empty, I print it out. Actually, I want to change this. I don't like this. I want to push the node onto the print stack. Tree node. Okay, where's the print stack? Where do I push? So you see, I was pushing current dot value. We are not pushing value anymore. We're pushing the current node, and result dot add print stack dot pop dot val. Okay, I hope this will not give me any errors. And run. Yeah, that was accepted. Let me submit. Excuse me. It should be yeah. It did well. Uh, that's the same as the recursive solution, same time. So, but this gives you better insight into what it means to be on the call stack, and then you are using 2 stacks to manage the actual call stack because you don't have return pointer 1 and return pointer 2. This is the trick to do this. And that concludes my explanation. If you have any questions about my explanation or would like to give any suggestions, please leave them in the comment. And otherwise, you have a good day.